Welcome. Let's try to solve another Leetcode problem 3233. Find the count of numbers which are not Spencer. Let's just try to understand what is a Spencer number. So we are given two positive integers L and R. For any number x, all positive divisors of x except x are called the proper divisor of x. So what is the meaning? Yeah, we don't need to understand actually. This is just a proper divisor. So a number is called Spencer if it has exactly two proper divisors. So what is the meaning? Oh, it means we have to understand the proper divisor. So all positive divisors of x except x are called the proper divisors. For any number, all positive divisors of x except x. So for example, if we are giving a number 4, what are going to be the divisors? It's going to be 1, 2, and 4. But we need to accept that x, accept that number 4. So 1 and 2 are called proper divisors, right? So for this number 4, yeah. So a number is called Spencer if it has exactly two proper divisors. So this number 4 is called Spencer because it has only two proper divisors, 1 and 2. But for number 2, for example, it has proper divisors only 1 because 2 is not a proper divisor. So 2 is not Spencer, but 4 is a Spencer. Yeah. So this is just the idea. So for example, 4 is a Spencer, but 6 is not Spencer because 6 has 1, 2, 3. It has 3 proper divisors. So we're going to return the count of numbers in the range L to R inclusive that are not Spencer. Okay, we solve this problem easily. So first of all, let's check what is a prime number. So for example, if we have a prime number 2, yeah, but 2 is not a Spencer number. But what about the 2 times the 2? So 4 is a Spencer number. Yeah, because for 4 it has factors like 1 and 2, but except 4. What about 3? 3 is a prime number, so 3 times 3 is going to be 9. So for number 9, it has the factor of 3 and 1. Yeah, so for this number 9, yeah, for this number 9, it has the factors of 1 and 3. So we're going to call it a proper divisor. Yeah, so this is just some of the definitions according to the problem. Yeah, so according to our guess, maybe if a number is a prime number, so the square of this number gonna be a Spencer number. Is that right? So for 25, we're gonna have the proper factors of 1 and yeah, we have the proper divisors of 1 and 5. Can we find another one except 25? We cannot. Yeah. Even though we cannot prove it, but it seems it is like that. If this number is a prime number, if the square of this prime number is inside the range of L to R, it means this is going to be a Spencer number. But we just need to count how many numbers which are not Spencer. I mean, it's going to be the total numbers minus the Spencer numbers. So for this case, it's going to be 3 minus 0. Yeah. Now let's just start coding. I think it's clear enough for us to solve the problem. So we're going to define E prime. So we're going to use Aristotle's algorithm to find how many prime numbers in an array. So yeah, let's just prepare a prime array. So we're going to use 4 times 2 plus 2 times n minus 1. I think everybody should know how to write this kind of code. Yeah, because it is the same pattern. If primes I, so we're gonna use another loop j inside of the range I times I to n plus 1, and the step gonna be I, and the primes j gonna equal to 4. Finally, we're gonna return. Yeah, we're gonna return the primes array. So this is the definition of this E prime. So we're gonna get a prime numbers array, and according to the index, we're gonna check if this number is a prime number or not. Yeah. Now we just need to check all the possible cases of prime number. let's just use this way, maybe for I. Maybe we're going to use a Boolean value. B is a Boolean value for IB in enumerate primes. So what is the primes? Let's just call the E prime, and we're gonna check. We're gonna check. Basically, we're gonna check how many numbers that is possible. We're going to use 10 to the power of 5 because this is 10 to the power of 9, so at least we're going to use 10 to the power of 5, so 1 after 5 zeros. Yeah, so this is our prime number, so we're going to check one by one. So if I times I more than equal to L less than equal to R, so we're going to count. So this is our counter, so we're going to count it. And finally, we're going to return R minus L plus 1 minus the count. Yeah, so we're going to set count to be 0 from the beginning. Yeah, so from here, this is all the possible prime numbers, and we're going to check the square value of this one. If it is a prime number, if B and B is a Boolean value, if this is a prime number, and its square value is more than or equal to 5, more than or equal to L, less than or equal to R, so we're going to count it. This means this is going to be a Spencer number. But we want to count return not Spencer. It means the total numbers minus the Spencer number is going to be all the numbers which are not Spencer. Yeah. Now let me just submit it to check if it works. As you can see, it works, and I think the speed is okay. And the time complexity is just O(n), and this n gonna be 10 to what is this n? Yeah, and this n gonna be 10 to the power of 5. Basically, it's gonna be a square root of this number. Yeah, so we're gonna set it 10 to the power of 5. I think it's enough for us to solve the problem. I think that's all about it. Thanks for watching. See you next time.